Yeah, slow and steady. Okay. I think I've already explained for how to design the chemical devices, okay, which is applicable also for the functional products. 4 steps you have to remember. First is to specify the product performance, okay, and then second is to identify the key ingredients. Okay, what is the key ingredient? For example, if you want to design the air purifier, right? Okay, the key ingredients is the catalyst, titanium oxide. Okay, because you want to decompose the volatile organic compounds. Similarly, also if you want to design the what is it? The granules or the herbicides. Okay, the key ingredient is what is the key ingredients? Okay, this one is for the functional products. Okay, and similarly, also if you want to design the moisture absorber, right? If moisture absorber, later we will do this tutorial together lah. This moisture absorber. I don't think we gonna I'm gonna explain the tutorials this one activity 5.2 because the solution is there already, right? Okay. And this one is moisture. Moisture absorber, yeah, yeah. The same lah. Okay, moisture absorber. Okay, how to design this one? Okay. Okay, moisture absorber. Okay, we will design this one. Okay. I don't think this one is in detail the solution. Okay. Okay. So what else? And then the third one is identify the physical chemical phenomena lah. How is the mechanisms, right? Okay, is it the catalyst is it absorb or just absorb or dissolve or absorb and then decompose or degrade the volatile organic compounds. Okay, that is the phenomena. Okay, and then number four is use the models or experiment available data knowledge. Okay, so if you still remember, for the what is it? For design the air purifier, right? Okay, what the model that you have to use? Okay, so it's including the kinetics, Fick's law, partial pressure, thermodynamics, all this information or knowledge you can consider depending on the what product that you want to design. Okay, so for today, okay. For today's, we will discuss. I will give lecture on the how to design the functional products lah. The same step or 4 step. Okay, 4 step. Okay, if you still remember. So this is the examples, which is to design a control release herbicide granules. Later we will do together for the moisture absorber. Okay, the moisture absorber is just what is it? The equation, isn't it? Is given. Okay, herbicides such as 2,4-D. Okay, this one is 2,4-dichlorophenoxyacetic acid are commonly used for killing unwanted broadleaf weed while leaving the desired crops to grow unmolested. Okay. However, herbicides spread on the soils are easily lost due to the leaching, volatilization, or biodegradation. Only some of the herbicide used to killing weeds. Okay. So there's a company want to develop a control release granules. Okay. So the phenomenon is this active ingredient can disperse within the polymeric matrix. Okay. So we can release herbicide at a very fast rate. Okay, at the beginning, and then after that is at the lower rate. Okay. So we can use for the long period of time. Okay. So the first step is to specify the product's performance. So this ones we identify from the experimental test. Okay. So the product performance should deliver 0.5 to 2.0 milligram per square meter per day. Okay. Milligram per meter square day. From day 1 to until day 10. Okay. followed by a lower dose, 0.1 to 0.5 milligram per meter square day, okay, from 11 to 90. So meaning that the totals that we can release the herbicide is until 90 days lah. Okay, what is the maximum that this herbicide can release actually? I think it's lower than that. Okay, thus the total maximum amount is around 60 milligram of herbicide lah, should be applied to 1 meter square of soil. Okay, so this is the area. Okay, so the product attributes is varying depending on the granule size, materials, and then also concentration of herbicide granules. Okay, um, this is the first step, which is to identify the product performance, and second is the key ingredients. Okay, so for the granules, okay, granules herbicides, we use cellulose and lignin. So the performance actually the release rate is different between cellulose and lignin. I think it's because of difference of the chemical structure and also the what is it the structure for lignin is more compact compared to cellulose. Okay, cellulose is just from the chain of the glucose, while lignin is the aromatics. Okay, I think the rate for the lignin is much slower than the cellulose. Okay, in releasing the herbicide from the granules. Okay. Okay, even if you do the decompositions, if you heat it, cellulose and lignin, okay, lignin rate is very slow, and cellulose is the reaction rate is much higher, okay, compared to lignin. Okay, so we can expect that this release rate actually based on the reaction rate. Okay, okay. So this is the two key ingredients. I think we can do the comparison between cellulose and also lignin. Okay. And then identify the physical chemical phenomena. This is a physical and chemical. Okay. The release of herbicide from the granule is controlled by two different mechanisms, which is dissolution, degradations, and also diffusion of the herbicide. Okay. First is the cellulose granules. Okay. This one is control the dissolution rate of the cellulose in the soil. And then second one is the lignin biodegradables. Okay. So if you look at here that they're using what is it? Dissolution rates equations. This one I think is more to the mass transfer. Okay, I'm not so really familiar with the mass transfer equations. Okay. But this one is a differential. Okay, mass transfer. Okay, because it's a dissolution rates, right? Okay. So this is a separation, more to separation process. Okay. So MC is the mass of the cellulose, K is the dissolution rate, and R is the radius. This one. Okay. MC along with the time. Okay. And then amount of dissolved cellulose, MCD. This one we do for the dissolution of cellulose matrix first. Okay. So can be obtained by the mass balance. Okay. So if you look at here that there's a density of the particles, XC is the weight fraction of the cellulose. So from this one, okay, and then we can get this one R equal to after integration 5.11, right? So just substitute this equation. Substitute this 5.13 to 5.112. Okay, so this we use a model. Okay, so you substitute to this equation. Okay, and then we can get the MH lah. Okay, the cumulative amount of herbicide released from the granules. Okay, so just substitute, we can get these equations. Okay, and then after that we can solve lah for the cellulose dissolution rates. Okay, by substitute all the parameters. This one K naught. Okay, K naught is the dissolution rate. Okay, and rho is the sensitivity. XH is the what is it? The herbicide mass fraction. Okay, just substitute. So we can get this profile. Okay, This is the radius lah, different radius. We test with the different radius, right? The herbicide. Okay. So if you look at here that from this profile, okay, so it's released too much within a few days lah. This one, see, it's reduced because the herbicide is released, but it's become maintained after around 20 lah. Okay, this is very slow lah. Okay, so it's released and sustained less than 25 days lah. Okay, meaning that is lower than 90 days. Okay, so if possible, if we can extend until 90 days is much better lah. Okay, rather than only 25 days. So we have to find the method, and also we have to recalculate again how can we release maximum is 90 days lah. Okay, rather than 25 days lah. So I think our target is more than 25 days lah. Okay. Okay, so this is a model dissolution rate for the cellulose. Okay, and the second step is look at here that diffusion rate, right? Okay, controlled by the lignin. Okay, so this is on the lignin. So for the lignins, we use a fixed law. Okay, so fixed law is also mass transfer, right? This one. Okay, I'm not really familiar with the mass transfer. Okay. So similarly also the concentration degradation. Generally, if we relate degradations or decompositions, okay, it should be related with the derivatizations. Okay, for example, like kinetics is a decomposition. Okay, so if the composition rate, so it should be related with the dx over dt lah. This one. This is a decomposition rate. Okay, so you have to remember anything that related with the decomposition or reducing the amounts, it should be with the rate. If chemical reaction kinetics, we call it a rate of reaction. Okay, maybe for the mass transfer or transport process is like what is it? Rate of release, rate of diffusion, all those things is the same. Okay. So this is the equations regarding on the for the lignins. Okay, this is and also the boundary. Okay, and we substitute into these equations. Okay, so that we can get the release the diffusion rates for the lignin. So if you look at here that the larger, what is it? The larger granules, right? Okay, this is a higher dosage. Provide the higher dosage. Okay, within the first 10 days. Okay, and the lower dosage is for the the small granules. Okay, 0.8. So meaning that the larger granule is much better than smaller, right? Because this one is released too much. Okay, so we need a much more amount of the granules rather than smaller ones. Okay. Okay, so that is the fourth step, similarly like chemical devices. Okay. Let's we do together the problem for the moisture absorber. And this one is I already revised. Okay. Okay. A home supplies company decide to produce a reusable moisture absorber product for removing the water content in air in an enclosed space. A reduction in humidity is expected to help inhibit growth of mold and mildew. Okay, fungus apa panggil biasa kalau if there's a suddenly berubah transition. Misalnya if the high humidity, if you in the closed system, right, macam closet kan, so if humidity tinggi dia akan ada macam fungus lah. Awak akan nampak putih-putih lah. Okay, itu biasa lah. Okay, kalau kat rumah pun at home you can check in your closet lah, especially if you have a blazer covered in the casing, right, or what is it, the coat, right? Okay, if been long time you didn't take out from your what is it, the closet, is there is some fungus on it. Okay, and move. As a measure of product performance, the moisture absorber should reduce the relative humidity of air in a closed code cabinet. Okay, code with dimension 2 meter times 1 meter times 1 meter lah, from 90% to 50% at 25 degrees. This one lah. Okay, if you look at here, A, okay, we do together this one. Okay, today we just focus on the functional products. Okay, and next week next class we focus on the formulated product. I give you the link for the jam board. Okay, go to page which page? Page 12. Okay. Okay. There are two common hygroscopic materials, silica gel and calcium chloride. Comment on their suitability as the raw material for the intended products, okay, for the closet. And what is the physical chemical behavior that govern the uptake of the moisture in the materials? Okay, can you discuss? Okay, I give you around 10 minutes. Okay, on the left side is the calcium chloride and the right side is for the silica gel. Okay, can you give a comments on their suitability? Comparison between the calcium chloride as well as the silica gel. Okay, and what is the physical chemical behavior? Whether it can, what is it? How they absorb the water actually, right? Because it's moisture, right? Okay, can you discuss? Please write the comment. Tutorial 5. Moisture observer. Okay, can you write? Anyone can start? I share. Jamboard. Share. Can you discuss? Okay. Right in the Jamboard. Low absorption capacity. No strong smell. High absorption capacity. Environmental safely. No corrosive. I don't think so. That is a good, what is it? uh, comment on the suitability of the intended product. Both I think is non-corrosive. What is the difference? Low absorption capacity, are you sure? For the silica gel, long period protective. Where we can use for the calcium chloride and silica gel? At where we can place this calcium chloride and silica gel? Where we can place? Silica gel usually you can place where? In moisture. Where we can place? Yes, high absorption capacity, yes, is correct for the calcium chloride. So in terms of mechanism of the absorptions, how? For the silica gel, extract more moisture, drying agent. Yes, of course, both is drying agent because it absorb moisture. Place in the very small piece, yes, short period of time. Okay, how about the calcium chloride? Where we can place? Okay, suitable for any type space is more effective and condense over longer period, right? Okay. So let me add here sticky note. Saya tak boleh ni, turun ni. Absorb much water. Much water. Okay, so this is mine. Okay, nampak? Okay. So readily form hydrates with moisture absorb much water and dissolve in a crystal. Used for shipping because it's cheaper, so we can use uh, much more compared to the what is it? Compared to the silica gel, okay, it's a much expensive lah. And a small piece for the foods, right? Highly porous, uh, sodium silicate. Uh, so, so, um, okay. Is regional. Okay, so this one is for the what is it? Silica gel lah. So if you look at here, okay, uh, right. Readily form hydrides with moisture absorbed in iron crystal, the water used for the shipping because it's cheaper, right? Okay, for the large space lah. But for the silica gels, porous because it's from formed from the synthetic silica sodium silicate. Okay, so the mechanism that uh, how the silica gel absorb the water is through the hydrogen bondings lah. Okay, with the surface of the hydroxyl functional groups. Okay, okay, that is one of the phenomena lah. Okay, another one is easily regenerated. Why? Because you can regenerate even in if you do the experiment or to absorb the moisture we're using a silica gel right? From the without the moisture, the silica gel color is gonna be a blue, like a blue color lah. Okay, once it's absorbed too much water until concentrate, so the color is become like a pink color. Okay, so and then we can regenerate. Just heat it the silica gel, so we can regenerate again the silica gels. Okay, to the original color lah. Okay, and then we use at a small enclosed space like a closet, food packaging, right? Okay. Sometimes food packaging also have a most oxygen absorber. Okay, to avoid the oxidation occur for the food, right? Okay. Even for in the laboratory we use silica gel rather than calcium chloride. Okay. So that is uh, the difference. Okay, between the calcium chloride and also silica gels. So this is the physical chemical behavior also lah. Okay. 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 And then next is let's see. Develop and solve. Okay. The model for determining the specification for these products. Okay. What is the minimum amount of the silica gel to lower the humidity to 50%? Okay. Okay, there's the information given here. Okay, just one number one, B1. Okay, B we don't have to do this one. Okay. So if based on the step, once we determine the key ingredient, the physical chemical phenomena is we have to apply the mathematical modeling, right? So this is a mathematical modeling, sah. Okay. So the information is the weight of water per unit weight of the silica gel is 0.26. This is usually we use a symbol L. This one is L. Okay, this is L. The symbol is L. Okay. Density of silica gels, the density is 2.64. Of course, is density is a rho lah. Okay, the density is rho. And then diffusion coefficient. Okay, the diffusion coefficient is 0.37. Okay, okay. So let's we do together this one. Okay, if you want to determine the amount of water absorber, meaning that the amount of water, this is a minimum amount of the water, MA lah, we use a symbol of MA lah. So we need the equivalent condition. Okay, so we need the first, we have to use the relative humidity equation. Okay, by using this equation. This one is not complete. Okay, we do together. So first, what we have to do is we calculate. Okay, so if you look at here, P is the partial vapor pressure. Okay, and P prime is saturated vapor pressure. So how to find this saturated vapor pressure? So we have to calculate by using Antoine equations. Okay, it's given already this one, A, B, C. If it's not given, okay, at 25 degrees C, you have to refer any chemical engineering handbooks. Like this one is, you can refer to thermo KK books, right? Okay, so if you calculate, okay, so this one, if you calculate, okay, P prime, can you substitute uh, into these equations? P prime, the answer. What is the answer? P prime. What is the answer? P prime. So just substitute. I give you a time. This one A, this one is B, and then this one is C. Temperature, this one 25 degrees C. T must be in this one. P is millimeter mercury. What is the answer? Can you give me? Anyone? A, B, C, and T. What is the log P? P lah, P prime. Let's calculate. Usually you're familiar with the Pascal, right? So you can convert in Pascal. What's the answer? So when you determine this P, you substitute into this one. Can you convert into Pascal? Is it 26.68? Okay, 26. Yes, 26. 23.69. 23.69. Can you convert to Pascal? Nila? 315. 315. That's correct. Okay, let's substitute into this equation. Okay, so it's given the relative humidity from 90% to 50%. Okay, so by using these equations, could you calculate the pressure for 90% and 50%? So meaning that, okay, wait, P initial is 90%, right? Equal to P I halve. Pi P initial lah. Okay, 90% lah. So Pi because 90 times with the P prime. P prime the one that you calculated already. Okay, so this one is 0.9 lah. Do also P final because your target is 50% humidity, right? So P final time with P prime saturated vapor. Can you calculate the answer? Also? What's the answer? PI and PF. Okay, PI 2842. Okay, 0.11. Okay, and then P 28 to 0.11 lah. Pascal. Okay. How about PF? PF 15. Yes, 15. Right. Okay. So this is the one. So since we know the ideal gas law, okay, why we use ideal gas law? Because 25 degrees C. Okay, and then the condition is just you just apply the what is it? The silica, the moisture absorber, right, in the closet or in the goods or for the food packaging. So I don't think the pressure is very high. So that's why we consider only uh, low pressure. Okay, unless if you uh, put in the reactor with the high pressure or high temperature. Okay, so that's why we just assume that we use the ideal gas law. Okay, it's water vapor, right? We want to absorb the water vapor. Okay, and then molar mass is 18 gram per mole, and then R is 8.314 lah. Okay, so next is you have to calculate the mass lah, a mass at the initial and also after the final. So you have to rearrange this equation. So for the mass for the initials absorber, uh, water lah. Okay, amount of water in the air and also amount of water finals lah in the air. Okay, because you want to absorb kan. This is for the water vapor, right? Okay, the moisture. So you rearrange for so we can get uh, P PI, right? Okay, for the initial V. Okay, V uh the dimension of the closet just now. Okay, we gave you to you already. Okay, M. Okay, divide by RT. Similarly, also you have uh, apply for the M finals lah, the moisture in the air. Okay, PF. Can you calculate? PM divided by RT. M this one, okay? 18. This one. M. This one M. Can you calculate MI and MF? Calculate. I'll give you 5 minutes. Can you calculate? MI and PI lah. Okay, what is MI and MF? Anyone? Okay, so MI is equal to, is given already, 41.3. And then MF equal to 22.94. Okay. Okay, so you can get. So this one MI. So total amount of the moisture absorbed, how much? So meaning that we use mm. Total amount of moisture absorbed. So mm. So equal to this one lah. Yes, 41.3 minus 22.29. Can you minus? How much you can get? Let's calculate mm. Okay. 41.30 minus 22.9 gram. 18.36. Okay, 18.36 gram. Okay, so you can get this one. Okay, mm. Okay, so since if you look at here that equilibrium moisture contents, okay, L, this one is given, right, 0.26, right? Okay. Of the absorbent, quantify the maximum amount of moisture that can be absorbed at a specific temperature and relative humidity. So meaning that this one is given 0.26. Mm is give we calculate already 18.336 kan. Can you calculate MA? MA is a what is it? Amount of moisture absorber. Okay, because we want to calculate what is it? We want to calculate uh, what is the minimum amount of silica gel, right? Okay, what is the minimum amount of the silica gel? Can you calculate MA? We can reduce 50%. Can you calculate? Nila? 70.62. Okay. Gram of silica gel. Okay. So this is the amount. Okay, if you want to reduce 50%. Okay. Any questions? So this is the step for the mathematical modeling that you have to apply, okay, to design your functionalist product. Similarly, also the chemical devices. Okay. So first you have to identify the product performance, second key ingredients, right? Product performance, just now you do the comparison, right? Okay. Key ingredients, what is it? For the silica gel, of course, what is it? Sodium silicate, right? But for the calcium chloride, of course, calcium and the chloride. Okay. And also the crystalline structure, the crystallinity of the calcium chloride. Okay, that is the key ingredients. Okay, and physical chemical phenomena, how they can absorb. Is it on the hydrogen bondings? Okay, or absorb in the crystallinity of the calcium chloride. Okay, that is the physical chemical phenomena. And then number 4 is you apply the mathematical modelings. Okay, so you can compare with other products. Okay. Okay, any question about these examples? Is it clear? Okay, mathematical modeling is, I think, is important. Thermodynamics, mass balance, energy balance. Okay. Any questions? Okay, this one is what is it? A formulated product. Formulated product. We discuss in the next class. Is it clear? Okay, right. Uh, tak ada banyak pun. Okay. So today I think is enough lah. Kita terlalu ke depan sebenarnya. Okay. I think we have another one chapter actually. Another one chapter. What chapter? Business decision making. This one is very short. I will give a lecture also. It's no need. This is my part. Okay, maybe within 1 week or 2 weeks, it's finished already for the business decision making. Okay, is it clear how to design the functional product? Clear, right? Okay. So that's all for today. I think it's just 1 hour. I think it's enough. Okay. So